Okay, 7-minute clip. I got something. Got interesting last night because here, chalk only with polystyrene, with production of reductive flammable gas, started to green up. You can still see the bubbles coming up. So there. And how long's that been? 13th of December, so it's Tuesday, so it's been a week exactly today, and it was 6 days yesterday, so interesting. So that's basically, normally it takes, if I did that in water without any polystyrene, it would take a month or 6 weeks, so it's about 4 times faster with the polystyrene in the water, I would say. So I've made up another one now, same thing here, as you can see, with the some phosphorus in the water. So 6 days, will it green up faster than 6 days, and will it green up better? And I'm thinking with these things whether I could actually eventually replace the popcorn with something simpler and cheaper, like sucrose, just common garden table sugar, because popcorn is a maize, which is by a grass, and as we'll see later on in this book, Phragmites australis, or Phragmites in general, has a very high lignin content compared to other things in there. And in the book it says that cation exchange capacity is proportional to the lignin content, and that's very strange because how can you have, in sphagnum peat, it's proportional to its lignin content, but peat has lignin in it apparently, but sphagnum moss doesn't, has no structural lignin in it. So where does the lignin in peat come from? That's another. See, there's another inconsistency again. More in, and it also says down here in the Principles of Nutrition there in A.C. Bunt and Alfred Daniel Hall. That's very good too. This is because the cation exchange capacity of materials is known to be pH dependent. Organic matter being more effective than clay. So there's another really basic important point. So last night I set up an iron one with the polystyrene, with no ammonia in it, and it looks like it's stable. The iron hasn't tried to rust like normally iron tries to rust. So in other words, the polystyrene in a way is acting like salt, because if you put a lot of salt with iron, that also stops it from rusting, as we learnt from that in that box thing in there. So I'm not going to get any response from the polystyrene in there because it's doing the same thing as the salt. But if I do it with the polystyrene and take the salt out, because we find that salt seems to degrade. Basically what I'm saying is all the little results are starting to come back, and we can actually project it forward, sort of thing. And so I set up just the copper and polystyrene and the phosphorus one there, so there's no salt in that one. And it was amazing, when I first made it up, it lost the blue colour, and it slowly came back within about an hour or so. So that was very strange too. So the only time I've ever come across when copper losing like its blue or green colours is when you mix it with alcohol, methylated spirits, and it goes to like a white colour. And I'm wondering, is it putting the copper into a organic sort of safer form? Is that what's going on in a way? We're turning copper into a more organically or more biologically acceptable form, sort of thing, that's not so toxic or not toxic at all. I don't know. Anyway, so I thought I'd do another iron one today, and I'd put some ammonia into it, sort of thing. So I'm just going to I'm in two minds about how to do it, fellas. Whether I want to I might as well put this on the stand, I suppose. The other thing is, I realised I didn't talk enough about the so we'll just move this around here. I realised I didn't talk enough about that bottle there, so I'll do that while I'm making this up. I didn't really get and convey the point, is by adding the nickel we were actually diluting the copper down to half its strength, and yet we kept the same colour. Do you understand what that means? So that sort of implies They're either increasing the ammonia content onto the copper, or the nickel somehow is causing the ammonia in here, whatever's in the particulate form, to actually go into the water and make the ammonia solution stronger, which makes the I'll put this in there. I don't know why I really should do it round the other way, you know, do the ammonia, give it a good old shake up for a few hundred times, and then add the irons in. But I suppose we're going to find out. We can always do it again. That's the whole thing about science. It should be reproducible, and you can do things more than once. So we're going to put the ammonia in, and the iron should go green to some extent, but it might not. As I said, we've learned from it has to. Oh, and by the way, I managed to get 421 pieces in here of about 1/8, you know, size of an inch sort of thing in here. So maybe this is a new YouTube challenge. How many bits of polystyrene can you get, you know, by hand? I mean, you could just grind it up and put it in that way. And what sort of volume occlusion do you have? So yeah, we found we do have to. Oh, it's starting to get a sort of grey green. Whoops, filled up too high. Bugger. Oh, there's lots. Anyway, so it would. Yep, grey green. That's the copper hydroxide being formed. Put that out of the way. Yeah. So we'll get the phosphate to go down. But that was the important point, is I forgot. I'll put that in there and make a nice screenshot. And the opposing colours, I think. I didn't really get that across, I think, that point, is the fact that you now got half the amount of copper in the solution, because you've doubled the volume, and yet it keeps the same colour. So what about the Beer Lambert law?